Welcome back. Here is an example to illustrate what we've been learning. A pizza parlor franchise specifies that the average or the mean amount of cheese on a large pizza should be 8 ounces. Standard deviation only zero point 0.5 ounce. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it is made with 6.9 ounces of cheese. Assume that the amount of cheese on a pizza follows a normal distribution. If the amount of cheese is below the mean by more than 3 standard deviations, the parlor will be in danger of losing its franchisee. All right. Let's standardize our score. We are told mean is 6 point, sorry, we are told mean is 8 and standard deviation is 6.5. Our inspector found the amount of cheese to be 6.9 ounces. So x minus mu over sigma. This is negative 2.20. So you need, if you are below 3 standard deviations, you are in danger of losing your franchise. Well, you are not below 3. Okay, so you are not in danger of losing your franchise. Okay, now you saw an example. How would you construct Z score? Now, suppose you are given the Z score. How would you find the X score? This is the formula. Z times sigma plus mu gives you your raw score back. All right. Standard normal distribution. What are the advantages of a standard normal distribution or the properties of a standard normal distribution? If the original distribution of X values is normal, then the corresponding Z values have a normal distribution as well. The Z distribution has a mean of 0 and standard deviation of 1. The normal curve with these properties has a special name. The standard normal distribution is a normal distribution with mean 0, standard deviation 1. Any normal distribution of X values can be converted to the standard normal distribution by converting all X values to their corresponding Z values. The resulting standard distribution will always have mean mu equals 0 and standard deviation sigma equals 1. Let's study areas under the standard normal curve. We have seen how to convert any normal distribution to the standard normal distribution. We can change any X value to a Z value and back again. But what is the advantage of all this work? The advantage is that there are extensive tables that show the area under the standard normal curve for almost any interval along the Z-axis. The areas are important because each area is equal to the probability that the measurement of an item selected at random falls in this interval. Okay, standard normal distribution can be tremendously helpful. Standard normal distribution mean is 0, standard deviation is 1. So 68% lives within negative 1 to 1. Negative 2 to 2 that's 2 standard deviations away from the mean. So that's 95% area will be under negative 2 to 2. Likewise, negative 3 to 3, you get area 99.7%. How do we use a normal standard distribution table? Here, using a table to find areas and probabilities associated with the standard normal distribution is a fairly straightforward activity. It is important first to observe the range of Z values for which areas are given. The range is usually depicted in a picture that accompanies the table. In this text, we'll use the left tail style table. The style table gives cumulative areas to the left. So let's figure out what they are talking about, right? You're looking at the table. The table is available, mind you, at the end of our lecture notes, both the volumes. All right. So here is table 3. These are the Z scores and these are the areas. For any Z score, the area given here is the left tail of it. Here is the Z score, that's they are positive, and the left tail is this part. All right. So now, however, Z values for which the range is depicted by the picture, we are using the left tail. Determining other areas under the curve utilizes the fact that area under the entire curve is 1, taking advantage of the symmetry of the distribution. So the procedures you learn for using left tail style normal distribution applies directly to cumulative normal distribution. Okay, so this procedure is similar to what is used in packages, computer software packages. Regardless, here is a concrete example how you would find area under the standard normal curve to the left of negative 1.0. So negative 1.0 is to the left of 0. You want to find this area. So what do? You look at your table, look for Z value negative 1.0. Negative 1.0 is here. All right. And there are many numbers here. So which number would you choose? For that, you go upstairs. So negative 1.0 is nothing but negative 1.00. This would be negative 1.01, 02. I don't need any of that. I would simply want negative 1.00. So that's the number you're looking at. Okay, that's the area. So all right, the column under Z, exactly what we spoke about, negative 1.0. That's the number. That's the area we are looking for. Okay. Now, if you want to find area to the left of 1.18, positive 1.18, so you're to the right. I'll go back to positive 1.18. So here is positive 1.1, that part. The 8 part, I go up and look here. There. That's the 8 part. Two places after the decimal point. That gives me 1.18. So 1.1 and correspond to the column 0.08. So 0.8810. Okay. Let's look at the table here. So 1.1, 0.08. So that's the number. That's the area. All right. We'll come on to, so let's review this procedure. To use the left, for the areas to the left of a specified Z value, use the table entry directly. Okay. For right area, look at the table value directly and subtract from 1. For areas between two values, say the bigger value, from the bigger area, take away the smaller area. All right. Take any area to the left of Z value smaller than negative 3.49 as 0 and Z value greater than this as 1. Okay. These are the limits of our table. If you notice, 3.49 is the maximum you have. All right. 3.49 is the maximum you have. So anything bigger than 3.4, you assume the area is 1. Likewise, anything smaller than negative 3.49, assume the area is 0. All right. We'll continue in our next video.